Welcome to Chapter 7 of Class 8 Science, Particulate Nature of Matter. In this fascinating chapter, we'll explore the fundamental building blocks that make up everything in our universe. We begin by observing everyday phenomena: why we can pile up stones but not water, why water takes the shape of our hands but loses that shape when released, and how invisible air can add weight to a balloon. These observations lead us to the revolutionary idea that all matter is composed of extremely small particles that we cannot see with our eyes. Get ready to discover the secrets of solids, liquids, and gases, and understand how ancient Indian philosophers like Acharya Kanad proposed atomic theory thousands of years before modern science. Let's begin by exploring what matter is made of. We start with Activity 7.1, where we break down a stick of chalk into smaller and smaller pieces. No matter how finely we grind the chalk, each tiny speck is still chalk. It doesn't transform into a new substance. This shows us that matter can be divided into extremely small particles that retain the properties of the original substance. In Activity 7.2, we dissolve sugar in water and discover that even though we can't see the sugar particles anymore, we can still taste the sweetness. This happens because sugar breaks up into its constituent particles, which occupy the spaces between water particles. These activities provide strong evidence that all matter is composed of a large number of extremely small particles that are not visible to the naked eye. Now let's understand what decides the different states of matter. The key factor is the strength of interparticle attractions, the forces that hold particles together. In solids, these attractions are very strong, keeping particles in fixed positions. In liquids, the attractions are moderate, allowing particles to move but keeping them close together. In gases, the attractions are very weak, allowing particles to move freely in all directions. It's fascinating to learn that ancient Indian philosopher Acharya Kanad proposed the idea of atoms, which he called Parmanu, more than 2,000 years ago. He believed that matter is made up of tiny, indivisible eternal particles, and this idea was recorded in his work called Vaisheshika Sutras. This shows the advanced scientific thinking in ancient India. Let's explore the solid state in detail. Solids have definite shape and definite volume because their particles are tightly packed with very strong interparticle attractions. In Activity 7.3, we examine various solid objects like iron, rock salt, wood, and observe that they maintain their shape unless we apply significant force. The particles in solids cannot move freely. They only vibrate or oscillate around fixed positions. When we heat solids, the particles vibrate more vigorously. At the melting point, the vibrations become so strong that particles start leaving their positions, weakening the interparticle forces and converting the solid to liquid. Different solids have different melting points depending on the strength of their interparticle attractions. Iron melts at 1538 degrees Celsius while ice melts at just 0 degrees Celsius. Now let's investigate the liquid state. Liquids have no fixed shape, but they do have definite volume. In Activity 7.4, we transfer water between containers of different shapes and observe that while the water takes the shape of each container, its volume remains constant at 200 milliliters. This happens because in liquids, interparticle attractions are weaker than in solids but still strong enough to keep particles close together. When you try to move your finger through water, you can do so without permanently breaking or cutting the water. The particles in liquids can move freely but within limited space. When heated, liquid particles move faster, and at the boiling point, their movement becomes so vigorous that they escape as vapor. Even below boiling point, some particles at the surface have enough energy to escape, This slower process is called evaporation. Let's now explore the gaseous state. Gases have neither fixed shape nor fixed volume. In Activity 7.5, we trap smoke in a gas jar and then connect it to another empty gas jar. After some time, the smoke spreads evenly in both jars, showing that gases expand to fill all available space. In another activity, we balance two identical balloons on a stick, then inflate one balloon and reattach it. The side with the inflated balloon goes down, proving that air has weight. The inflated balloon contains more air particles, making it heavier. In gases, particles move freely in all directions with very weak interparticle attractions and very large interparticle spaces. This makes gases highly compressible. When pressure is applied, the particles come closer together, reducing the volume without changing the mass. Now let's understand how temperature and pressure affect the states of matter. Temperature has a profound effect. Heating can convert solids to liquids, melting, and liquids to gases, boiling, while cooling can reverse these processes. Pressure mainly affects gases. Increasing pressure can compress gases and even convert them to liquids, liquefaction. This is how LPG is stored in cylinders, as a liquid under pressure. Changes between states of matter are reversible physical changes. The chemical nature of the substance remains the same. Water can exist as ice, solid, water, liquid, or steam, gas, depending on temperature and pressure conditions. Understanding these transitions helps us design many useful technologies from refrigeration to power generation. Finally, let's explore diffusion and evaporation. Diffusion is the process where particles of one substance spread out and mix with particles of another substance due to their random motion. We observe diffusion when perfume fragrance spreads throughout a room or when ink spreads in water. The rate of diffusion depends on the state of matter. Gases diffuse fastest, liquids slower, and solids slowest. Higher temperature increases diffusion rate as particles move faster. Evaporation is the process where liquid changes to vapor at temperatures below its boiling point. It occurs only at the surface and causes cooling because the particles with highest kinetic energy escape, lowering the average kinetic energy of remaining particles. This is why we feel cool when sweat evaporates from our skin. As we conclude this chapter, let's review the key concepts and their real-world applications. We've learned that all matter is composed of extremely small particles that are in continuous motion. The arrangement and movement of these particles determine the three states of matter: solids with definite shape and volume, liquids with definite volume but no fixed shape, and gases with neither fixed shape nor volume. We've explored how temperature and pressure cause changes between these states, and we've understood diffusion and evaporation processes. Most importantly, we've learned about Acharya Khanad's ancient atomic theory that predated modern science by thousands of years. This knowledge helps us understand everything from why LPG is stored as liquid under pressure to how refrigeration works. Remember that understanding the particulate nature of matter is fundamental to all sciences.